A plastic water bottle can survive being crushed, frozen, and refilled. Yet it started as a black, tar-like liquid pumped from underground. A plastic toy can snap into hundreds of tiny identical pieces, but it began as loose-colored powder, not a solid at all. A plastic bag can hold 10 pounds of groceries and stretch without tearing, yet it's thinner than a human hair. That shouldn't be possible from something that starts out looking like oil and dust. Three completely different objects, all born from nearly the same starting point. So how do factories turn crude oil into bottles, toys, and bags trusted by millions of people every single day? Let's step inside and find out. A plastic bottle looks simple, clear, light, disposable, but every bottle on the shelf started as raw petroleum, thousands of miles from any factory that makes packaging. Getting from crude oil to a bottle you can crush in one hand takes a chain of chemical transformations most people never think about. It begins at an oil refinery, where crude oil is heated and separated into different fractions based on how heavy or light each part is. One of those fractions, naphtha, is sent to a petrochemical plant. There it's broken down or cracked using extreme heat, splitting large hydrocarbon molecules into smaller, simpler ones. This process produces ethylene, a simple gas that becomes the building block for the plastic used in most bottles, PET or polyethylene terephthalate. Ethylene is combined with another compound derived from petroleum, purified terephthalic acid, inside massive reactors that can stand several stories tall. Under carefully controlled heat and pressure, these molecules link together in long, repeating chains, a process called polymerization. It takes hours for the reaction to fully run its course, and engineers monitor the mixture constantly because even a slight imbalance in temperature can produce a resin that's too brittle or too soft to hold its shape later. The result is a thick, honey-like resin that's cooled, extruded into long strands, and cut into small pellets, no bigger than lentils. Some plants blend in recycled PET at this stage too, sorting and cleaning old bottles until the flakes are pure enough to be melted back down and folded into new batches of resin, right alongside virgin material. Those pellets are shipped to bottle factories around the world, where they're dried to remove any trace of moisture, then melted down and injected into small, tube-shaped molds called preforms. They look almost like test tubes with a bottle cap already threaded on top. The preforms are reheated to a precise, narrow temperature window, just soft enough to stretch, but not so soft that they collapse, then blasted with high-pressure air inside a bottle-shaped mold. In under 2 seconds, the softened plastic stretches to fill every corner of the mold, forming the final bottle shape, ridges and all. The bottles are cooled instantly, trimmed of excess plastic, inspected by high-speed cameras for any defect invisible to the human eye, and sent down the line to be filled and capped, sometimes at rates exceeding 1,000 bottles per minute. Here's the part most people miss. That blow molding step happens so fast and under such tightly controlled pressure that a single degree of temperature difference can cause a bottle to warp or burst on the line. Factories run automated sensors checking wall thickness thousands of times an hour, because a bottle that's even slightly too thin in one spot won't survive shipping, let alone a trip through a hot car or a crowded backpack. Even the cap and label go through their own quiet chain of precision. The cap is molded from a slightly different plastic, polypropylene, chosen because it can flex thousands of times without cracking. Every time someone twists a bottle open and closed, that hinge or thread has to survive the stress without splitting. Labels are printed separately and wrapped around the bottle at high speed, aligned within a millimeter or two so the barcode scans correctly at checkout every single time. From crude oil pumped out of the ground to a finished bottle on a truck, the entire journey can take as little as a few weeks. Turning something you'd never want to drink into something designed to hold the water you do. A plastic toy starts even stranger, as a fine colored powder that looks more like sand than a solid object. Plastic toys seem simple, a few interlocking pieces, bright colors, maybe a snap-together design. But turning raw plastic into a toy precise enough to click perfectly into place every single time requires tolerances closer to what you'd expect from aircraft parts than from a toy aisle. Most toys start with a different plastic than bottles. ABS, or acrylonitrile butadiene styrene, valued for its strength, its glossy finish, and its ability to hold fine detail after cooling. It arrives at the factory as small colored pellets, already tinted to the exact shade needed. Engineers match colors using digital color codes, so a red piece made this year matches one made a decade ago, down to a fraction of a shade. Before melting, the pellets are also dried in large hoppers, since even a trace of moisture trapped inside can create tiny bubbles that weaken the finished piece. The pellets are fed into a hopper and melted at temperatures around 450 degrees Fahrenheit. From there, the molten plastic is forced under enormous pressure, sometimes tons per square inch, into a steel mold engraved with the exact shape of the toy piece, down to fractions of a millimeter. These molds are often machined from solid steel blocks, a process that alone can take weeks, because the mold has to be built to survive millions of cycles without wearing down or losing its shape. The mold snaps shut, plastic floods every cavity in a fraction of a second, and cooling channels built into the steel mold pull heat out almost immediately, hardening the plastic from the outside in. Within 10 to 20 seconds, the mold opens and the finished piece is ejected. Still slightly warm, but already holding its final shape. Robotic arms often pull the parts free and stack them for inspection, since a single production run can produce tens of thousands of identical pieces in a single day, all expected to match perfectly. Here's the detail most people never consider. The connector studs on interlocking building toys are held to a tolerance of a few thousandths of a millimeter. That precision is why a piece made in one country in one decade still fits perfectly with a piece made somewhere else years apart. One tiny miscalibration in the steel mold, and millions of pieces from that batch simply won't click together, which is why molds are checked and remeasured constantly throughout a production run. Before any of that happens, though, every new mold goes through an exhaustive testing phase. Engineers run thousands of trial pieces, measuring each one under a microscope and checking how it clicks against pieces from older molds, sometimes going back years, to make sure nothing has drifted out of spec. Only once a mold passes that testing does it get approved for full production. The finished pieces are tumbled to remove rough edges, inspected under bright, even lighting for color consistency, then bagged or boxed for shipping, a process repeated millions of times over to fill toy shelves worldwide. A plastic bag takes the opposite approach. Instead of a solid mold, it's stretched paper thin from a bubble of air. A plastic grocery bag weighs almost nothing, costs almost nothing, and yet can hold several times its own weight without tearing. That strength to thinness ratio comes from a manufacturing process that looks more like blowing a giant balloon than shaping plastic at all. Bags are typically made from polyethylene pellets, either high-density or low-density polyethylene, depending on how rigid or stretchy the final bag needs to be. Like the other plastics, it starts as resin pellets delivered from a petrochemical plant, sometimes mixed with recycled material, depending on the product. The pellets are melted and forced through a circular opening called a die, forming a thin tube of molten plastic. Instead of pulling it into a mold, factories pump air into the center of that tube, inflating it like a giant bubble, sometimes stretching 20 feet or more into the air above the factory floor. As the bubble rises, it cools and thins dramatically, stretching the plastic down to a fraction of its original thickness, while air continuously supports its shape from the inside. And rollers at the top gently guide it upward without letting it collapse. Once cooled, the tube is flattened and wound onto large rolls that can weigh hundreds of pounds, spinning continuously so the line never has to stop. From there, it moves to a separate machine that cuts the film to size, seals one end shut, and often punches out handles, all in a single automated pass, producing hundreds of bags per minute. The part that surprises most people: the plastic in a typical grocery bag is stretched so thin during the bubble process that it's often under 20 microns thick, thinner than a human hair. Yet the way the polymer chains align during that stretching is exactly what gives the bag its strength. If the bubble cools unevenly, the bag tears the moment it's loaded, which is why factories monitor bubble thickness with laser sensors in real time. Even the handles are engineered more carefully than they look. The plastic around each handle opening is reinforced slightly during the cutting stage, since that's the exact point where nearly all of a bag's weight gets concentrated the moment it's picked up. Skip that reinforcement, and a bag that looks identical on the shelf will tear the first time someone tries to carry it home. From resin pellets to a roll of finished bags can take just hours, turning something as unglamorous as petroleum into a product engineered to stretch, hold, and carry without anyone giving it a second thought. That's how plastic bottles, toys, and bags all go from crude oil and colored pellets to the objects sitting in your kitchen, your toy box, and your grocery run. Precision, pressure, and chemistry most of us never think about. Until now. If you enjoyed seeing how it's made, hit subscribe and join us for the next deep dive into the everyday objects you never think twice about.